disintegrating and so on, so we get the same energy behavior. We then talked about the mass energy equivalence. We introduced Einstein's famous equation E equals mc squared to say that if we can convert a certain amount of mass into energy, then because the mass is multiplied by the speed of light squared, 3 times 10 to the 8 squared, then we can produce enormous amounts of energy by converting very small amounts of mass. And we then looked at the atomic masses of various substances of interest. So things like neutrons, protons, helium, hydrogen, and the heavy elements such as uranium and plutonium. And how basically when we fission heavy atoms such as uranium, the sum of the masses of all the components, or sum of all the products, are actually slightly less than some of the masses of uranium and the original neutron. And it's this mass difference that actually gives us the energy. That's amazing. We then looked at interactions between neutrons and nuclei, so things like scattering, interaction, inelastic and elastic scattering, and the capture interaction where basically the neutron is absorbed by the nucleus, and that can have two outcomes. One is the neutron either stays in the nucleus just becomes slightly heavier, or it through decay can transmute to something else, or it can fission. The neutron goes with the nucleus tries to rearrange, and it can't, and then it becomes so unstable that it splits into two or more fission products, two on average. So once we've introduced this concept of fission, that capture out fission, we can now look at nuclear reactions with neutrons. So we look at things like breeding reactions where you absorb a neutron into uranium-238, which becomes, by Neptunium-239, becomes plutonium-239. We also looked at fission reaction, leading to the production of two fission products plus 2 or 3 neutrons. And through the concept of binding energy, we can then use that reaction via the atomic masses of all the products from that reaction. We can then calculate how much energy is liberated by that reaction. And I've handed out some tutorial exercises today which have reactions of that kind of form on them, where basically you calculate the mass difference between the reactants and products, and convert that mass difference into an energy release. We then looked at the idea of critical chain reactions. So the neutrons produced by one fission reaction then go on, or at least one from a fission reaction goes on to produce another fission reaction. And we looked at the conditions necessary such that only one neutron from each fission reaction survives to make another fission reaction. And that's termed a critical reaction. And we measure how far we are away from criticality using a quantity called reactivity. If the reactivity is 0, it means we have a critical reaction, which means the power is increasing or decreasing with time. If the reactivity is negative, it means the reaction is subcritical, and it means the power is diminishing with time. The power of the neutron population is diminishing with time. And if the reactivity is positive, it means the neutron population is increasing with time, and therefore the power is increasing. We also touched on the role of later neutrons in achieving criticality, and also extending the time scale over which these neutron lifetimes actually occur. So it's a time scale between such a fission event to give us a chance of actually controlling the reaction. So, and then finally we touched on neutron motion and reactor control. So within neutron motion we looked at why we use moderators in a thermal reactor to actually slow the neutrons down to increase the likelihood of fission. And we then looked at the various influences on reactivity, such as the coolant effects, temperature effects, and reactor poisoning. So that kind of was a quick tour around the physics lectures. We then looked at nuclear installation safety, and most of this was about definitions. Probably the most important definitions you need to remember are the objectives, the nuclear safety objectives, the fundamental safety functions, which are basically removal of core heat, control of reactivity, and confinement of radionuclides. So it's basically 3 C's: control, confinement, and cooling. And sometimes it's called chemistry as well. Not chemistry, but generally we set it as the 3 C's. Then we moved on to design principles. Interestingly, I have a slightly different list of what Tim had, which is quite embarrassing. The first one I talked about was single failure. The fact that no single failure or no single operator reaction should compromise a fundamental safety function. And then talked about diversity, which Tim has already talked about, so that if we have a single failure of a component of a particular type, if we have another component providing the same function but operating with a different principle, then that's a diverse system. So if you need to provide a cooling water flow, for cooling, if you have 2 pumps, one pump is electric and the other one is diesel, then that's 2 diverse means of actually pumping the water. Redundancy is basically just having more than one of something. So again, if one pump will provide the duty, then we provide 2 pumps, so that if the third pump fails, so that's redundancy. Segregation, which I think Tim called independence, which is basically having all your systems not located in the same place in space, but also not coupled through things like common control systems, common power supplies, and things like that. So to have each system as independent as possible, both in terms of its location and its functional relationship with the other systems as well. They also have fail-safe, which was the idea that you could say, for example, set traffic lights failing, you want all the lights to fail on red rather than on green. It's inconvenient, but at least not everybody thinks they've got the right way. I didn't have a testing that Tim had, so that's quite an interesting one, which I'll have next year. We looked at acceptability of risk. So basically, where risk is very subjective, different people tolerate certain levels of risk differently, so it's not an absolute measure of risk. And also risk has to be tempered against benefits and also against consequences as well. Or I guess risk is the consequences. It's the likelihood of an event happening versus the consequences of it happening. And I think the example I gave, at one end you could have something which has got a very high probability of happening, which is say spilling a cup of coffee on yourself, but the consequences are generally relatively minor. Whereas the opposite end of the scale is being struck by lightning. So it's a very rare event, but the consequences of being struck by lightning are actually quite great. But most of us tolerate either end of that spectrum. We'll drink coffee without really worrying too much about spilling on ourselves, and also we'll go walk around in thunderstorms and things like that without being worried too much about being struck by lightning. So it's the whole sort of likelihood versus consequence spectrum which comes into the assessment of risk. We then talked a bit about defensive depth, about having multiple layers of safety. Each one has to be challenged independently, if you like, before you get all the way through to an important failure. I think I've seen something recently which was quite an interesting analogy where someone talked about the Swiss cheese model, where you look at each of your defense layers as a slice of Swiss cheese with holes in it. And if you stack several slices of Swiss cheese up on top of each other, then it's only where the holes line up that you have potential accident pollution layer. A certain event can challenge each layer of the defensive depth. What we try to arrange is that each of our layers of defense, whilst not being entirely complete, will have holes which don't necessarily line up with the other ones. And that's kind of the art of it, if you like, is trying to ensure that you have all of the holes not lining up. So the idea is, for example, if you look at containment of fishing products, we've got, as Tim said before, we've got the first line of defence is containment of fishing products in the pores of the fuel. The second line of defence is the cladding of the fuel pin. The third line of defence is the pressure boundary of the primary circuit of the reactor. And the fourth line of defence is the containment itself. You could argue the environment is the fifth line of defence if you move the population part from the reactor. But generally, you've got five levels there by which you have fishing products reach the people. So that pretty much covered nuclear installation safety. We then looked at thermal hydraulics. So the properties of different coolants, and Tim covered quite a lot in his lecture and his revision session, where we're looking at gaseous coolants, water, liquid metals in particular, looking at the neutronic and the chemical characteristics of those coolants. We talked a little bit about flow networks, about how a reactor itself is actually quite a complicated flow structure with many parallel flow paths, some intentional, some leakage paths, some accidental, or opportunistic, I should say, rather than accidental. One example we used of flow networks was the definition of flow gagging, so that we can control the temperature distribution across the core outlet, varying the amount of flow that goes up each of the fuel assemblies in the core by independently changing the hydraulic resistance of each fuel element using the gas. We then touched on heat transfer, in particular how the heat transfer requirements depend on which coolant you're actually using. So for things like water and liquid metals, we tend not to do anything to enhance the heat transfer on the fuel pin surfaces. We have smooth fuel pins, and we don't need to do anything else because we've got high enough heat capacity and we've got high enough conductivity to get efficient curing. Somebody earlier said that gas coolants were fairly poor coolants in comparison to liquid water or liquid metals, and that's true. And we talked about how we enhance heat transfer when we're using things like carbon dioxide in the advanced gas cooled reactors, or again carbon dioxide in magnet reactors, either by using chains or by buffering the surfaces to increase the turbulence and increase the heat transfer. We then went on to core design. Effectively, core design is the integration of everything I've talked about up to that point, plus material selection considerations, both from mechanical and corrosion point of view and from neutronics point of view as well, and also the mechanical design of the core as well. So looking at mechanical stability, seismic resistance, and so on. We then looked at fast reactors, in particular what fast reactors are for, and the idea of fast reactors to close the fuel cycle, to be able to make their own fuel in the form of plutonium, and then to be able to continue that cycle by breeding more plutonium. So basically the case for fast reactors hinges on the fact that less than 1% of all the uranium in the world is actually usable in reactors, and if we want nuclear power to be sustainable in the longer term, we have to go to closed fuel cycles and reactors which can convert uranium-238 into plutonium at least at the same rate as which they're burning fuel in the first place. So that's the case for breeding. And then we looked at the various architectures used to do that. The main characteristics of a fast reactor is we need to conserve the neutron energies. So we want to cut down the distances that the neutrons have to travel and minimize the amount of matter with which they interact. So we have a very small, compact core with very high power density, and this then necessitates the use of a very efficient coolant, such as liquid sodium. So we then looked at the architecture of a sodium-cooled fast reactor and talked about some of the longer-term options for fast reactors, such as gas-cooled fast reactors and lead-cooled fast reactors. So, and then finally, we finished off the lecture series with a look at fusion reactors, and we concentrated on the near-term fusion reaction, which is the deuterium and tritium reaction. We covered this a bit in the physics lecture as well, the actual reaction itself, but we covered it in this lecture. And then we looked at some of the practical problems such as the tritium fuel in the DT reaction isn't naturally occurring. We have to make it, we have to breed it in the reactor. So we looked at things like the breeding of tritium from lithium-6, in dedicated breeding blankets. And these also provide a means of actually removing the heat from the reaction as well, from the reactor as well. The plasma itself, even though it's at 100 million degrees, is almost invisible. It's almost invisible across the spectrum. So we don't get a huge amount of radiant heat actually coming off the plasma. Most of the energy comes off in the form of fast neutrons, and we use the breeder blankets to capture the energy of those fast neutrons to fission lithium-6 into tritium, and that reaction also liberates heat, which we can reduce by coolant and then use that to generate electricity. So that was the sort of main engineering challenges, well not engineering, but the main sort of challenges of where do we get the fuel from, how do we remove the heat, and then we looked at the rest of the architecture, such as the vacuum vessel, the magnet systems, and things like that. And I think that's it for me. Thank you very much. And I say, Andrew said of examples and solutions together. Try and do the examples together, looking at solutions, but if you need to look at the solutions, then they're there together.
It's all friendly.
I've got 4 things really to do today. Firstly, to remind you about the 3 main things that I have talked about. Of course, the first of those was the Big 4 accident, which was only last week. Several people actually asked, well, that lecture was fun. What I should know, each accident occurred because of misunderstandings in the science or engineering, as I explained. So we looked in detail at each incident and actually what happened in it and the lessons we've learned from it. The lessons we've learned from it are extremely important. So this time I've learned, so I think I'll get over sting on that. So that session was actually so recent that I'm not really going to speak about that again today, but I'm happy to take it up with a question. The main thing I want to talk about really is obviously the gas-cooled reactor and the materials in them. And now it's finished messing up the screen. I have 2 little slides to introduce that. It's related to things that I've read in the newspaper this week. And I'll wait to get back to that. In the meantime, I impersonate Andy Jones for a short while. Stop there. What's going on? Come to Andy Jones later. Right, 2 things from the Times newspaper this week. As it says, it's going to be grim. I know it's grim up north, it's kind of down south, but it's going to be grim. Things are not going well. I talked about President Sarkozy being unelected this weekend, and it duly occurred. Mr. Hollande is going to spend money that France doesn't have already on yet more projects, and in order to get some of that money, he's going to take money away from other organisations such as EDF. Now, EDF owns EDF Generation Limited, which runs 14 AGRs in this country, does it not? It's also planned that EDF and Centrica together are going to build half of the new water reactors in this country. The other half, well, the consortium that we're going to do that has withdrawn already because the two major constituents in it are German, and the German government is becoming increasingly anti-nuclear because of Fukushima and because of austerity. So RWE, Nuchem and E.ON have withdrawn. That took half of our potential gigawatts away. EDF, which doesn't have any money anyway in France, then was forced because of Fukushima to take a really hard look at their first European pressurised water reactor at Flamanville, which is now 4 years late. They have realised, having done the stress tests that were demanded by the IAEA after that Fukushima accident, that it is a safe reactor, which is we all knew all along. But they decided the price is probably going to be 40% higher than they thought to build in the United Kingdom, which obviously is not good news. 2 days later, another headline, which really just shows to make matters worse. So the article actually deals with the electricity situation in the United Kingdom. Now, I'm not going to go into all that now, we must focus on the AGRs, but one of the issues, which I didn't really raise before, is relating to coal generation. We did speak about carbon capture technology, and the fact that it works on small scales but hasn't yet been proven on a large scale. Think about how much CO2 a coal-fired power station generates. You've got to get rid of it very efficiently, very quickly, and very successfully. In 2018, 11% of our electricity generation in this country, by law, has to close down. That's 3 large coal-fired power stations in the Trent and Aire Valleys, very British, very Eggborough, because they cannot and will not be installing carbon capture technology by 2018, which Brussels has demanded. So in principle, we either defy Brussels and keep the lights on, or we turn off 11% of the available generating capacity in the UK. By then, we will certainly not have any more nuclear, even if we started tomorrow. I've got that on track. It's not possible before around 2020 or 2021. So, we've got 14 AGRs still running and 1 PWR. 14 AGRs need somehow to keep going longer and more effectively than they have. What are the main issues, then, that we need to address to keep AGRs going longer?
Showing that they're going to be safe.
Showing that they're going to be safe. Yeah, anybody else?
Graphite aging.
Didn't hear that. Couldn't see who it was.
Graphite aging.
Graphite?
Aging.
Aging? Right. Let's develop graphite aging a bit. What are the things that are going wrong with graphite? How does it age?
Oxidise.
Oxidises how?
Radiolytically with the...
Radiolytic oxidation, did you say? Yeah. Anybody else want to tell me a bit about radiolytic oxidation? Why is it a problem?
It affects the strength of the carbon reactor.
Yeah. Anybody else wants to get involved in this debate? You're all going to be addressing questions in this exam, which may well be on AGRs, or at least one of them might be. Maybe any more than that. So, we've got radiolytic oxidation going on in graphite. Let's go a bit back. We're all hiding again. What happens in radiolytic oxidation exactly? Anybody want to tell me? You thought you were safe up here, didn't you? Nobody's looking in the eye. Do I pick on somebody? Sir, tell me about radiolytic oxidation. It reduces the strength of the graphite, yeah?
Changes its shape.
Right. Changes its shape. No, that's wrong. We'll come to what changes its shape in a minute. Taking material away, that's the important thing. Porous, gas in the pores, oxidising through ionising radiation. Graphite turns to a gaseous product is no longer there. Yes, strength is reduced. Okay. Now, somebody, yes, changes its shape, somebody said. What causes graphite to change its shape? Right, radiation damage. Do you want to elaborate? Somebody? He's doing quite well. Come on. Tell me something about radiation damage. Yes.
It changes its shape.
We've been there. Right, go back to first principle. What happens that causes radiation damage?
Displacement of carbon atoms from the lattice.
Somebody, sorry?
Is it displacement of carbon atoms from the lattice?
You displace the carbon atom from the lattice by what?
Neutron radiation.
Neutron radiation. That's a funny phrase.
Neutron bombardment.
Neutrons. I'll settle for neutrons. I'll settle for fast neutrons. I won't settle for neutron radiation because that's a sort of silly phrase that people who don't understand what they're talking about would use.
I said irradiation studies.
Yeah, okay. So we're displacing the carbon atoms. Where do they go? Well, where do they come from, first of all? Somebody tell me what a graphite crystal looks like. I've seen somebody doing this. Yeah. What's the word for one of them? Hexagons, yes, right, okay. Layers of hexagons. So carbon atoms are getting pushed out of their places in the lattice. Carbon atoms are getting pushed out of their places in these hexagons, right. They're going into other places, so the crystal changes its shape. Right, now we're moving towards radiation damage of graphite, aren't we? Okay. Let's go back to radiative oxidation for a moment. What's the product of the radiative oxidation? What's the gas that's reacting with graphite? Somebody must know that. Carbon dioxide. Okay. Carbon dioxide plus graphite equals what? Carbon monoxide. Yeah. Okay. What is one of the consequences of the build-up of carbon monoxide in the coolant in an AGR? Frog's getting in the way with this now. I'm going to descend. So we're generating carbon monoxide in the reactor, in the coolant. What's the consequence of that?
Moderator. Neutron absorber.
Is it good or bad? Someone say bad? Why? You're not allowed to point, you mates. But since he said bad, why did you say that? Because it's wrong. Well, it's mainly wrong.
Does it inhibit further?
It inhibits further oxidation. Yes, it's good. 1% of CO takes out half of the oxidation rate. But it is bad for another reason. So do you want to get a Browning point back again by telling me why that is? The D word. Deposits. Soot. Forming in places where it interferes with heat transfer. Okay, now then, how do we control the concentration of carbon monoxide in the coolant? And the secondary question, why do we need to control the concentration of carbon monoxide in the coolant?
With methane.
Sorry, didn't hear that?
With methane. Methane gas.
No, we'll come to methane gas. Park that one, and I'll come back to you. But I'm asking a question about carbon monoxide. How do we control its concentration, and why do we?
Using sulfur.
Sorry, again?
Is it by using sulfur?
By using
Sulfur.
sulfur.
Yeah.
Sulfur. No. We're going down the wrong track.
Low temperature.
I couldn't believe what I was hearing then.
Higher.
Small concentration of sulfur compounds stop carbonaceous deposition. But no, think globally. Think of the whole reactor now. We're generating carbon monoxide due to the oxidation of graphite core. Okay. That CO is going to go in the coolant. If we do nothing, there'll be more and more of it. That's not acceptable because our colleague up here pointed out that it forms carbon deposition. Okay, so what are we going to do? That was the original question.
Lower
What are we
temperature.
going to do to stop that happening? What piece of plant are we going to look at? Who's in there?
Filter it.
Sorry?
Can you filter the carbon dioxide as it comes out for a soot particle?
Yeah.